Hello students, in today's class we are going to see about the modern train controller. Formalism for the system design. Here we are using Unified Modeling Language as the formalism for the design. So here the Unified Model Language describes a design in terms of interacting object rather than the piece of codes. So it is the visual language that can be used to capture all the design tasks. So here the UML language consists of a different level of abstraction, that is creating requirements, verifying specification, architecturing the system, and designing the code, designing the test. The human language is very useful because it encourages the design by successive refinement, and it progressively adding the details to the design rather than rethinking the design at each level of abstraction. So it can be classified into two types. One is the structural description, another one is the behavioral description. So the object-oriented design under the structural description, and the state machines are the example for the behavioral description. So it can be described in the way that is closely models the real-world object and their interactions. So the object-oriented specification provides the basic set of primitives that can be used to describe the system with particular attributes. Best example for the UML language is model train controller. So rather than explaining the piece of code with the model train controller, we are going to see lot of interacting objects of the model train controller. This is the general structure of model train controller. In this structure, we are going to control the speed of the train. So we are about to control up to 8 train on the same track. So we are going to control the speed using the console box. The console box is the control box where the user can have it in the hand. So the control box consists of a throttle. The throttle is responsible for controlling the speed of the train, and the emergency stop button, and then inertia button. Inertia button is responsible for responsiveness of the train. So here, after sending the commands in the control box, it will send to the train through the tracks. So the track can receive the message from the control box, and it will send to the receiver in the train through the packets. Here the packet consists of header, address, command, and error correction code. So the receiver inside the train receive the packet from the track, and it control the speed of the train using the command which is set on the that packet message. So it is used to control the motor speed of the train. So what is the requirement to build this model train controller? So these are some of the requirements that we have seen already. So we will see the sample requirement form for the model train controller. So the name of the unit is model train controller. The main purpose of the design is we are going to control the speed of up to 8 trains. And the inputs of the train is throttle, inertia setting, emergency stop, and train number. The output of the model train controller is train control signal. The main function of the train is to set the engine speed based upon the inertia setting, and it has to respond to the emergency stop button which is pressed in the control box. So the performance of the train should be updated, and we have to update the train speed at least 10 times per second. Then the manufacturing cost is $50, and power needed for this unit is 10 watts. The physical size and weight, the console should be comfortable for 2 hands, approximately the size of standard keyboard. The weight is less than 2 pounds. So the next is digital command control. The digital command control standard was created by the National Model Railroad Association to support inoperable digitally controlled model train. So it defines the way in which how the model trains and controller communicate. It leaves many system design aspect open and allowing the competition. So we can classify the standards of digital command control into two. One is the electrical standard, another one is the communication standard. So the electrical standard defines how the bits are encoded on the rails. The communication standard defines how the packet format and schematics. Now let us see how the bits are encoded in digital command control electrical standard. Here a key requirement is that the data signal should not change the DC value of the rails. The data signal swings between two voltages around the power supply voltage. So as shown in figure, the bits encoded in the time between transition, not by the voltage signal. A 0 is at least 100 micrometer second, and the 1 is nominally 52 microseconds. The duration of high and low parts of the bit are equal to keep the DC value constant. The specification also gives the allowable variation in bit times that conforming the DCC receiver must be able to tolerate. So this is the basic packet format of the DCC. So here the packet format consists of PSE into SD plus E. So here the P stands for preamble, which is the sequence of at least 10 1 bits. The command station should send at least 14 of this 1 bit, some of which may be corrupted during transmission. So S stands for the start of the packet. It is always 0 bit, and S represents the address of the data byte that gives the address of the unit with the most significant bit of the address transmitted first. An address is 8-bit long. Then small s stands for the start of the data byte, which is like the packet start bit, which is always 0. And D stands for the data byte, which include 8 bits. The data byte may contain an address, instruction, data, and error correction information. So E represent the end of the packet, which is 1 bit. Next we will move on to the conceptual specification. So before we create a detailed specification, how the interacting objects are communicating. So what is the outlay structure of the model train controller, that we are going to see now. So the basic commands of the control box should be a speed setting and inertia setting and emergency stop button. So the parameter command name is for set speed. It is speed, and it can be a positive value or negative value. For the inertia, so it is the responsiveness of the train. So high inertia means there will be a low response to the controlling the train speed. So it must be a non-negative value. And emergency stop button. So this is a class diagram of your controller messages. So there should be a command. So there is 3 things in the command, that is the speed setting, inertia setting, and emergency stop setting. So the train control system turns the commands into packet. There are 2 major subsystems. One is the command unit and the train board component. So in that command unit, we are going to set either speed or inertia or emergency stop button. So this is the typical control sequence diagram of the model train controller. There are 2 subsystems, main subsystems. One is the console box, another one is the receiver. Here the main aim of console box is to read the state of the front panel, and it has to format the messages and it has to transmit the message. So here the another main subsystem is train receiver. So it should receive the message and interrupt the message according to the command received. It has to control the train. So this is the console system class diagram. So the console got panel, formatter, and transmitter. So the panel is responsible for reading the control box through the knob, and formatter is responsible for converting the reader message into the bit stream, and transmitter is responsible for transmitting message to the receiver of the train. And this is the train system class. So from the receiver end, what are the classes available? So it starts from the train set. So our main bowlers, we are going to control up to 8 train on the same track. So the train set represents the train number. So on which train we are going to control on the same track. So it consists of 3 major subsystems. One is the receiver, then controller, then interface. So the receiver is responsible for turning the analog signal on the track into the digital form, and the controller is responsible for controlling the behavior of the command, and figures out how to control the motor. And the motor interface is responsible to generate the analog signal required to control the motor. So here there is a number, that is numeric number 1 1, which means that there is a two-way communication. So the receiver sends message to the train, and the train send back messages to the receiver end. So up to which we have seen the conceptual specification. So detailed specification we will continue in the part 2.